Hi everybody, this is the second part of our lesson on double integrals over rectangles, and this video is going to focus on the topics of iterated integrals and the average value of a function. Okay, so starting with iterated integrals. Our goal is to learn how to integrate functions with two or more variables and how to interpret those results. So the main idea is to focus on one variable and integrate as usual, viewing all other variables as constants. Now notice this is similar to what we did in chapter 14 when we were taking partial derivatives, right? We would focus on a single variable, use all of our old derivative rules, and treat any other variable in the function as a constant. So we're hopefully a little bit used to this idea. Now, if we see the integral of f of xy dx, it turns out that the dx is the most important part of this integral. It tells us that we're going to integrate with respect to x and treat the y as a constant. Similarly, if we see an integral of f of xy dy, then the dy is what tells us that we're going to integrate with respect to y and treat x as a constant. Now, I actually really love this because back in our Calc 1 days, it's really easy for us to forget about the dx, the dt, the du, and leave off that notation entirely. But we see now in the multivariable setting how important that piece of notation is. It's now the most important part of the entire integral because it's what's telling us which variable is important and which other variables to treat as constants. All right, so let's look at some examples. Let's start by integrating the function 2x squared y plus y squared dy. So we're going to focus on the y. So that first piece, the 2x squared, will treat like a constant. So the 2x squared will simply tag along, and the integral of y is 1/2 y squared, plus the integral of 4y squared, which is 4/3 y cubed. And since this is an indefinite integral, we of course need a plus c. We're going to clean up that 2 and that 1/2 to simplify our answer to x squared y squared plus 4/3 y cubed plus c. All right, now a quick note on that c. This constant c is a constant as far as y is concerned since we're integrating with respect to y. So in this context, that c could be a function, a c of x, any function with x alone, right? As far as y is concerned, sine of x or e to the x, those would all be constants as far as y is concerned. So when we say a plus c in this context, that could be c of x, any function that only contains the variable x. All right, now let's integrate that same function, but this time let's do it with respect to x. So we'll focus on the variable x and treat any y's like they're constants. So when we integrate 2x squared, that will become 2/3 x cubed, and that y will tag along like a constant. And then plus the 4y squared we treat like a constant, so it will integrate to 4y squared times x. Since it's an indefinite integral, we need a plus c, and in this context, the c here could be any function that only contains the variable y. Okay, so these are some examples with indefinite integrals. What about definite integrals? So what about the integral from 0 to 1 of 4xy plus 12x squared y cubed dx? So we're integrating with respect to x. So when we do that, we will get 2x squared y plus 4x cubed y cubed. And we're going to evaluate the variable x from 0 to 1. So we start by replacing all of the x's with the number 1 minus what we would get if we replace all the x's with a 0, which in this case is just 0. So our final answer is 2y plus 4y cubed. Great, let's integrate that same function, but this time from 0 to 2 with respect to y. So integrating with respect to y, we would have 2xy squared plus 3x squared y to the fourth. So again, we treated all the x's like constants and just integrated the variable y like usual. We're going to evaluate y from 0 to 2. So we replace the y's with the 2 to get 2x times 4 plus 3x squared times 16 minus, if we replace the y's with 0, we would just get 0. So our final answer is 8x plus 48x squared. Now, notice, if we integrate a function of x and y with respect to x and evaluate the definite integral, then we're left with a function of y alone. That's what we saw in example 3, right? We did a definite integral with respect to x, and our final answer contained only the variable y. And vice versa. In example 4, we did a definite integral with respect to y, and our final answer contained only the variable x. So this observation is what we use to evaluate what are called double integrals or iterated integrals. Let's do some examples. So here we have a double integral. We're integrating the function 4xy plus 12x squared y cubed, first with respect to x from 0 to 1, and then with respect to y from 0 to 2. Now, I'm going to be a little bit lazy here. We started with that inside integral. And that inside integral, the integral from 0 to 1 with respect to x, that's the exact integral that we did in example 3. And we saw that in example 3, that inner integral is going to integrate to 2y plus 4y cubed. So letting that outer integral tag along, we get the integral from 0 to 2 of 2y plus 4y cubed dy. Now we integrate with respect to y to get y squared plus y to the fourth, and evaluate y from 0 to 2, gives us 4 plus 16 minus 0, or a final answer of 12. Great. Now what about in the other direction? Same function, but this time we're going to integrate with respect to y first, and then with respect to x. Well, again, I'm going to be a little bit lazy because that inner integral, that integral with respect to y from 0 to 2, is the exact integral we had in example 4. And we saw that it integrates to the function 8x plus 48x squared. So the inner integral becomes 8x plus 48x squared, and we let the outer integral from 0 to 1 with respect to x just tag along. So now integrating with respect to x, we get 4x squared plus 16x cubed. Evaluating x from 0 to 1 gives us 4 plus 16, or 20. All right, now right about now you should be asking yourself a big question. Notice that we got the same answer of 20, whether we integrated first with respect to x or first with respect to y. And the question you should be asking yourself is, does that always happen? Well, the answer is Fubini's theorem. And it tells us that if f is a continuous function on a rectangle R, then the double integral over R is the same value whether you integrate first with respect to y and then x, or first with respect to x and then y. So Fubini's theorem tells us that if the function we're integrating is continuous on that rectangle that we're integrating over, then it does not matter which order we integrate with. Whether we do y first or x first, we'll get the same answer in the end. Here is an example for you to try. So I would really encourage you to pause the video and work through this example on your own and see if you get the same answer that I got. You can even try doing both orders, x first or y first, and confirm that you get the same answer either way. When you're done, you can compare your answer to mine and see if you also get the answer of 12. Great. So that's a nice introduction to iterated integrals, but there's one more thing we're going to chat about in this video, and it's average values. So recall in the single variable setting that the average value of a function f of one variable defined on the interval from a to b is 1 over b minus a times the integral from a to b of f of x dx. So to get the average value of a function, we simply do the definite integral of that function and then divide by the length of the interval. In a similar fashion, we can define the average value of a function f of two variables defined on a rectangle R to be 1 divided by the area of that rectangle times the double integral of the function over R. So we simply do the double integral and then divide by the area of the rectangle. Let's do an example. Let's find the average value of the function 4 minus a half x minus a half y over the rectangle with x ranging between 0 and 2 and y also ranging between 0 and 2. So here's our formula for the average value. We're going to do the double integral of our function over R and then divide by the area of R. And there's a picture of our rectangle. So we see that the area of our rectangle is 4. So we'll have 1/4 times the double integral. It does not matter, according to Fubini's theorem, whether we integrate first with respect to x or with respect to y. So I've chosen to do y first, but you would get the exact same answer if you integrate with respect to x first. Okay, so that 1/4 outside is going to tag along, as well as that outer integral. We're going to focus on the inner integral, the integral with respect to y. So integrating with respect to y, we have 4y minus a half xy minus 1/4 y squared. So notice the 1/4 and the outer integral simply tag along, and we just did that inner integral treating y as our variable and looking at any of the x's as a constant. We evaluate y from 0 to 2, and that gives us 1/4 times the integral from 0 to 2. When we plug in y equals 2, we get 8 minus x minus 1. And then when we plug in y equals 0, we get 0. So now we integrate with respect to x. 8 minus 1 is a 7. So when we integrate with respect to x, we'll get a 7x minus a half x squared, evaluating from 0 to 2. And we get 1/4 times 12, or a final answer of 3. So the average value of this function over the rectangle R is 3. Great, that's all for this video. In our final video from this section, we're going to look at some more complicated iterated integrals, integrals that involve u substitution, for example, and see that although Fubini's theorem says that in theory it does not matter whether we integrate with respect to x or y first, we'll look at some examples of integrals where we may want to choose the order strategically in order to make life easier on ourselves. That's in our next video. I'll see you there. Bye, guys.